Okay. Today I am going to explain Unit 5. Unit 5 nano devices. That means we move to the next unit, nano devices. From this, now we are going to see one question, that is explain the electron density in bulk materials and size dependence of Fermi energy. So first understand the question. Question is explain the electron density. What is mean by electron density? What is mean by this electron density? That means the availability of electron in bulk materials. How dense the electrons are there in a materials. Electron density in a material and size dependence of Fermi energy. We know Fermi energy, that is Fermi energy level. It is the highest energy level where the electron occupied. So I'm going to explain about these terms: electron density and size dependence of Fermi energy. First we are going to find the electron density in bulk materials. For finding that electron density, first we are going to see about the definition. The definition of this electron density. Electron density is nothing but it is defined as the number of electron per unit volume in a material. So electron density is a number of electron per unit volume in a material. It is going to be determined with the help of the energy state, the help of density of energy state. That means definition is the number of electrons per unit volume. What is electron density? Electron density is defined as number of electrons per unit volume in a material. It is determined with the help of energy state, density of energy state. So that's the definition. Now we move to the density of energy state. Density of energy state. What is the meaning of density of energy state? The density of energy state density of energy state per unit volume. Density of energy state per unit volume for an interval E and E plus dE is density of energy state for an interval E and E plus dE of a material can be determined by using a formula Z of E into dE is equal to this formula, that is 4 pi divided by h power 3 into 2m power 3 by 2 e power 1 by 2 into d. the density of energy. So the electron density is going to be determined based on the density of energy state. What is a density of energy state? Density of energy state that is per unit volume between the energy level E, energy interval E and E plus dE is defined as, or it's going to be determined with the help of Z of E into dE is equal to 4 pi by h power 3 into 2m 3 by 2 into e power 1 by 2 dE. So 4 pi by h power 3 into 2m power 3 by 2 e power 1 by 2 into dE. Then also we have one formula, that is the help of the Fermi-Dirac distribution. One formula is there, that is f of E that is equal to, f of E is equal to 1 by 1 plus e power E capital E minus EF the whole divided by kt. This is a expression to find the probability of electron, the probability of electron in that energy state, probability of electron in that energy state, probability of electron that occupation in that energy states. So what is the meaning of these two equations? The first equation, that is nothing but density of energy state, that means density of energy state per unit volume between that interval, energy interval E and E plus dE is, that can be expressed by using this formula. And the probability of electron in that energy state is find out by using this formula f of E. These formulas, everything already we explained and derived in the previous unit. The previous unit we derived this. So these are the two formulas. Now our aim is to find the electron density. Then how to find the electron density? Already told, electron density is a number of electron per unit volume in a material. That can be find out by just product of these two, product of this energy state and this probability of electron occupied in that energy state, that gives electron density. That means electron density can be find out, or electron density available for conduction, electron density or electron that is available, density of electron that is available for the conduction in a bulk material, conduction in a bulk material. What is the meaning of availability of electron? If there is excess of electron is there, there will be conduction. So that's the mean. Electron, number of electron or density of electron that is going to be conduct in the particular bulk material can be find out by using this formula, that is Ne, that means number of electrons per unit volume in a material, that is expressed by the formula Ne is equal to Z of E into dE f of E. So this is a formula, that is the product of energy, that means energy state, and the probability of electron and the corresponding integration, energy band. So this is a expression to find the electron density, the number of electrons available for conduction in a material can be find out by using this formula in E is equal to integration of Z of E dE and F of E. Now that is, we know this value N of E is equal to integration of 4 pi by h power 3, then 2m power 3 by 2 e power 1 by 2 dE into 1 by 1 plus e power e minus ef by kt. Here k is nothing but Boltzmann constant. K is nothing but Boltzmann constant. Further, here we put one small e, that is effective mass of electron. Effective mass of electron. So this is a expression. So when you are getting integration of this one, you can get the electron density. So we know then wherever the integration is there, then definitely we should use some, that is limit value. Here the limit value is that energy band. So this is the equation to find this equation that gives that energy, that is electron density in a bulk material. And at 0 Kelvin, the probability of electron available is equal to unity. Why that one is unity? Because at 0 Kelvin, you look at this is going to be 0, temperature 0, it's 0, then automatically the value is going to be infinity, that is unity. So at 0 Kelvin, the probability of electron available in that particular that is material, and that is equal to unity. So now we see about the next one, that is how we are going to take the integration of this particular. Then energy band, simply you are putting energy band. Then what about the real value of this limit? The limit, we have that limit, lower limit and upper limit. The lower limit 0, the upper limit is EF. EF nothing but Fermi energy level. Then energy band, instead of energy band we can substitute 0 and EF, that is at 0 Kelvin. That is a expression to find the number of electron available in a bulk material per unit volume. So instead of this energy band we can substitute 0 and EF. That is so after getting the integration we can get the final value, that is the value which gives the electron density in a bulk material, that is Ne. After getting the integration, you can take the integration. As a result of integration, you can get this 8 pi by h power 3, that is 3 h power 3 into 2me star and e f power 3 by 2. This is the answer for finding number of electron per unit volume, that is electron density in a bulk materials. Here H is a Planck's constant, M is a effective mass, F that we know Fermi energy level. So electron density in at 0 Kelvin can be obtained by integrating this equation, that means the previous equation. After integration, this is the answer. So now we go and see about the total number of electron available in bulk material. Now one question is, what is the meaning of this equation? This is the equation to find the number of electron available per unit volume. Now we are going to find the total number of electron for an entire volume of a bulk material. For that, we are going to find that is total availability of total number of electrons for a whole material, that is N is equal to Ne into that is volume. The previous one is number of electron per unit volume. This is number of electron for the whole volume of a given bulk material. So now we know that is N, capital N is Ne, already we know 8 pi by 3 h power 3 into 2 me star and Ef power 3 by 2 into volume. How to find this volume? Actually, volume means length, breadth, height. Here, if you take the dimension of the material is A, the dimension of material is A, or side of material is A, then automatically volume becomes A power 3. So here we substitute A power 3. So this is the equation. This is the equation to determine the total number of electrons that available in a bulk materials. That is the expression. So now we move to find the that is size dependence of Fermi energy. The size dependence of Fermi. This is a electron density. This is the expression for electron density in bulk materials. Now we are going to find the size dependence of Fermi energy. Size dependence of Fermi energy. So the second part now. Size dependence of Fermi energy. So far we completed the first part, electron density. How much electrons are there in a bulk material per unit volume, and as a whole, how much electrons are there. Now we move to the next part, size dependence. That is Fermi energy. What is Fermi energy? Fermi energy is a highest energy level. Highest energy level that is occupied by electron. Highest energy level that is occupied by electron. That is at 0 in this way, at 0 Kelvin. 0 Kelvin, we know that the Fermi energy level value EF is equal to, that is 3 Ne by 8 pi power 3 by 2 h power 2 divided by 2m. That means EF is directly proportional to Ne power, that means 2 by 3. Sorry, that is here instead 2 instead 3, it is 2 by 3. That is this is Fermi size dependence of it. What is Fermi energy? Fermi energy level is a level that is highest energy level of the electron occupancy. That is electron occupancy at 0 Kelvin. That can be found out by using formula EF is equal. That this is derived from the previous equation. EF is equal to 3 Ne. You know that is Ne is a energy density. That is electron density. Ne is a electron density, already found out. Then H, M, everything, you know, M is mass of the electron. So this is a Fermi energy value. Next we move to the size dependence. where the Fermi energy level is there. In where the Fermi energy level is actually there. So here now up to this over now, what about Ne? Ne means energy density, that is Ne depend upon Ne means N divided by V, that is equal to capital N divided by A power 3. That is from this capital N is number of electron for a whole material. Small Ne is a number of electron per unit volume. So number of electron per unit volume is defined as number of electron as a whole divided by volume. So Nb. So now instead of Ne we can use this. So the equation becomes Ef is, that is proportional to N divided by A power 2 by 3. That is Ef is proportional to, that means already we know, that is A power 3, N divided by A power 3, the whole power 2 by 3, that means N divided by then power, that means N power 2 by 3 divided by A by 2, or we can write like this 1 by A power 2. Okay, 1 by A power 2. So why here we put this 1 by A power? Already we told that N, capital N is a constant. Capital N is a constant. But A is not a constant. Here A is variable based on the dimension. A, that is A into A, length into breadth into height. That is nothing but volume. Volume of the material, bulk material is going to be variable. Volume of the bulk material is going to be variable. So you can write Ef proportional to 1 by A power 2. That means the Fermi energy depends on the size of the material. The size of, if size of material is high, this Fermi energy level is, or size of material is increases, Fermi energy level decreases. That is the meaning of this. Now from this we are going to discuss where the Fermi energy level occupied in the case of metal, that means conductor, and where the Fermi energy levels are occupied in the case of insulator and semiconductor. In general concept, that means temperature that is T greater than 0 Kelvin. At temperature the T greater than 0 Kelvin. This Fermi energy, actually this Fermi energy level Ef is lies exactly, that is bottom of conduction band. Suppose this is a conduction band and this is a valence band. Conduction band and valence band all more or less overlap in case of metal. In case of metal, these two are overlap. In case of metal or in conductor, this Fermi energy level is occupied the bottom end of, or bottom of this conduction band. The bottom of this conduction band. Then in case of semiconductor and insulator, this Fermi energy level, this Ef is lies in that energy gap, or the middle of this conduction band and valence band, in between this conduction band and the valence band. That is for insulator and semiconductor. Okay. So this in case of semiconductor and insulator, this energy, that is Fermi energy, is in between this conduction band and valence band. And in the material and the metal, already told, the Fermi energy level is the bottom of conduction band. As further temperature increases, that Fermi level may enter into the conduction band. As temperature further increases, the conduction, that means Fermi energy level enter into the conduction band in case of metal, that means conductor. And insulator, semiconductor, normally says that it is located in the middle of conduction band and the valence band. Next, the spacing between the energy state. The spacing between energy state. The spacing between energy state that can be determined, that can be explained by this one, delta E. Spacing between energy state, that is also inversely proportional to that is cube of this size, that is side, or that is inversely proportional to volume. Inversely proportional to volume. That means as size this A increases, that spacing is going to be decreases. That means spacing will be decreased. Spacing between energy state. Spacing between energy state is inversely proportional to this cube of this side. That means spacing between energy state is increases. Spacing between energy state is increases. The size is going to be decreases. So that is the inference of this. So what is the use of this size dependence of Fermi energy? That in this heading we are going to find the location of the availability of Fermi energy level in case of the conductor, insulator and semiconductor, and also the spacing between energy state. So everything can be explained. Everything depends on the size of the material. So bulk material, the electron density different, and low size material, that electron density will be different. Then availability of the presence of Fermi energy level is also going to be changes based on that size of that material. That is the inference of this question answer. So the question is, explain electron density in bulk materials and size dependence of Fermi energy. So electron density already derived, that is for bulk material. In that case we derived two equations, that is one is Ne nothing but the number of electron per unit volume in a material. Then capital N, that is a total number of electron available in a whole, that means for a whole materials. So this is for per unit volume, this is for a whole size of the material. Then we talk about the size dependence also. So size dependence, which says that that is energy difference, space between the energy state is going to be inversely proportional to cube of the side, or inversely proportional to volume or size. As size increases, the spacing between energy level is going to be decreases. That is the mean. So now we come to this conclusion of this question. Now this is the question number 1. That is first question of unit 5, nano devices. In the next video you see the second. I am going to teach the second question answer in the next video. So thank you.